All right, so we've gone out and we see that the Big Bang model has two great triumphs. The first is it predicts that there should be a cosmic fog all around us. And when we go out, we see this fog, the cosmic microwave background, the place where the universe went from being hot and ionized to being cooler and neutral. So that is a great part of why we believe the Big Bang theory is correct. But the other thing that the Big Bang theory predicts is that the universe acts as a giant nuclear reactor when it's very young, when it's a few hundred seconds old. And it goes and predicts that there should be 25% of the universe should be helium, there should be trace amounts of deuterium and lithium. And we go out, and when we look in stars and we look in places, very primitive places in the universe, we once again see that the theory predicts what we see. So it's looking pretty good to me.
But that still leaves us with the biggest problem of the all, which is, why did the Big Bang happen in the first place? Why did the whole kit and caboodle start? Who pressed the big red button? And there's a real problem with this, because we have two great theories of 20th century physics. We have quantum mechanics, which deals with small things, and we have relativity, which deals with massive things. Normally you never need both. If you're going to deal with where Jupiter is tomorrow, you use relativity. If you're going to deal with a silicon chip, you use quantum mechanics. But there are two situations where you need both, where you have something that's both very massive and very small. One is the Big Bang, whole universe, no size. The second is actually black holes, not quite as big, but still very high densities. And the trouble is these two theories don't match. They have quite different mathematical underpinnings. They're like oil and water, they just don't go together. We know that when we go back to the very, very early universe, there can't be a true representation. Quantum mechanics gives you different answers from relativity, and they both make no sense. Presumably, there is some better, deeper theory, what we'd call a grand unified theory, a gut, or a theory of everything, a toe, which behaves like quantum mechanics when things are small, and behaves like relativity when things are massive, and behaves all like itself when things are both massive and small. But we don't know what this theory is, and without a theory like this, we can't tell where the Big Bang came from.
But we can go and test, can't we? We can go through and use the Large Hadron Collider and collide together particles with an energy of 14 TeV, so that's 14 times 10 to the 12 eV. So that means that's like looking at the universe when it's 10 to the 16 times smaller than it is right now. Or we could even go out and look at these really high energy particles that occasionally hit the Earth. Those are as big as 10 to the 20 eV, or that corresponds when the universe is 10 to the 23 times smaller than it is. Surely we should be able to get something from that.
Well, presumably that's giving us a sense of what the universe was like at these very small scales, but of course you can always go further back. So if we can look at how these violent cosmic rays behave, that gives us some idea of what matter behaves when it was 10 to the 23 times smaller than now, but when it was 10 to the 24, 10 to the 25, 10 to the 30, 10 to the 40, 10 to the 100. This is a real problem, and there are far too many grand unified theories out there. There are lots of very smart theorists, and they've come up with a wide variety of grand unified theories, but there's nothing to test them. We don't have a black hole in our lab, which is probably a good thing. So far, at the energies we've reached, at the Large Hadron Collider, the existing theories work fine. We haven't got to that combination of massiveness and smallness where we need a new theory.
So it really does come down to sort of a philosophical exercise, doesn't it? Because we can always, at least in the Big Bang theory, make the universe a bit smaller than what we can measure. And so we really do have this quandary, is how are we ever going to figure out how the Big Bang started? Because we can always push things to a point where our physics that we understand here on Earth breaks. And so I have to admit, to me, it's hard to say never, but it's hard to imagine how we're ever going to solve how the universe was created. Because even if we do figure out how, what happened at the Big Bang, then what were the conditions that allowed the Big Bang to happen? Clearly something had to be existing. There had to be physical laws, and what allowed those to exist? So it seems to me that there at some level is an intractable problem, is you can always take the thing back to whatever created whatever you've just figured out.